Hello, my name is Daniel Lemire. I'm a professor at the University of Quebec, and I'm going to tell you about our work on processing Unicode strings at gigabytes per second. Our goal is to read, validate, and convert Unicode strings at record-breaking speeds using practical software. Our work is supported by production-quality open-source software. Our code works on mainstream processors such as Intel, AMD, ARM, and so forth. Our goal is to process billions of characters per second, or conversely, to use less than a nanosecond per character. This joint work with Müller, Kaiser, and many others. Unicode is the de facto standard for presenting strings in software today. It's interesting to reflect on how such a standard came to be. We can trace back the need to represent characters and strings as sequences of bits to at least as far back as the Morse code. Under the Morse code, we might represent the letter A as a dot and a dash, the letter B as a dash, a dot, and a dot, and so forth. The Morse code was convenient to send data over a wire, but it's less convenient on computers. It's relatively difficult to decode because it has the granularity of a single bit. Over time, we developed many different other data formats that use a lesser granularity. For example, we had Bodo code that use 5-bit words, Ullrich code with a 6-bit words, and more recently the American Standard Code for Information Interchange, or ASCII code, that use 7-bit words. With 7 bits, ASCII can represent up to 128 characters. ASCII is a widespread standard. Essentially, each character is mapped to a given integer value. These integer values are sometimes called code points. What we call a character is not necessarily visible characters. In ASCII, we include so-called control characters, such as tabulations, line returns, and so forth. Unfortunately, we cannot represent all possible characters using ASCII. And different vendors have been tempted to produce their own standards. IBM proposed its own character encodings, for example. Various non-English language users also felt the need to introduce different character encodings. ISO 8859 is a family of standards that cover many European languages. The same thing happened with Thai, Indian, Chinese, Japanese, and Vietnamese users. They produce their own encodings. This diversity made software more difficult to write and created difficulties for users. Conversion between these different encodings was often lossy. Having a vast number of formats tends to lead to bugs, security failures, and so forth. Thus, people sought to create one interoperable standard that could be universal. Unicode was meant to be this new standard. It arose in the late 1980s. It extends ASCII in the sense that the ASCII table is a subset of the Unicode table. Whereas standards like ASCII or ISO 8859 represent characters without any attempt at sophisticated typography, Unicode provides an extensive support for typography. Furthermore, whereas ASCII is finite, Unicode is meant to be somewhat extensible. Every year we have new characters. For example, we recently added support for the pregnant person emoji. The intention behind Unicode is to make all other characters encodings effectively obsolete. In practice, it's succeeding very well. Each year, Unicode becomes more and more dominant. Initially, the authors of Unicode thought that using 16 bits would be more than enough. After all, most existing formats were at most 8-bit formats. However, they wanted to meet their goals of creating a universal character encoding standard, so they would need more room to do so. They planned for a bit over 1 million distinct characters. It implies that it would need, if using a flat number of bits per character, 21 bits. Unfortunately, processors do not operate using 21 bits, So we need different formats. So instead of this impossible or unpractical 21-bit format, we create a few distinct formats. There's a single Unicode table, a map from code point values to characters. However, there are many ways to store the code point values in bytes. There's a 30-bit 2-bit format that is not used very much for data interchange because it's wasteful. It's mostly used internally. In practice, we find that UTF-16 works with 16-bit words and UTF-8, which work at the granular byte. The UTF-16 format is widely used under Windows and is a common default in the programming languages Java and C#. The UTF-8 dominates web. It's a default for XML. It's required for JSON when doing data interchange between systems. It's a common default for HTML. It's also the default in many recent programming languages like Go, Rust, and Swift. Thus, while Unicode did become universal and did replace many different standards, we are still left today with two popular binary Unicode formats, UTF-8, which works on bytes, and UTF-16, which works on 16-bit words. They're both concise ways to represent characters, but they strike a different balance. For ASCII inputs, the UTF-8 format uses a single byte per character. Compared to 2 bytes per character for UTF-16, this often helps UTF-8 be more concise for content that is mostly ASCII, such as many HTML, XML, or JSON documents. For what I call Latin characters, they both use 2 bytes. For what I call the Asiatic range, UTF-16 has a slight edge using 2 bytes against 3 bytes for the UTF-8 format. Thus, for documents containing mostly Japanese or Chinese text, UTF-16 might be slightly more concise. Both formats use at most 4 bytes per character. Because the UTF-8 format is byte-oriented, it can be used for null-terminated C strings, since those are normally byte-oriented. And of course, UTF-8 is binary-wise backward compatible with ASCII, which is convenient. Most strings with UTF-16 can be assumed to use a flat 16 bits per character, unless we have some special characters like emojis, in which case your characters may record 4 bytes. However, though it seems like a feature that's proven to be error-prone, many software applications are unfortunately written as if characters were all 2 byte long. When programmers make this assumption, they open themselves to security bugs. This is why UTF-16 is sometimes discouraged. Before we discuss how we can manipulate Unicode data, it's important to review the formats. UTF-16, as the name implies, is organized as a sequence of 16-bit words. For code point values that fit within 2 bytes, we use precisely 2 bytes. We simply store the code point value. That is, we use an integer value spanning 2 bytes. For larger code point values, we use 4 bytes. The 16-bit words can be written in 2 orders, big endian or little endian, depending on whether the first byte in a 2-byte sequence contains the most significant or less significant bits. A common default is little endian, which matches our current systems that use Intel processor, for example, which means that the less significant bits come first. To store large code point values, we need 2 16-bit words. There's a range of code point values that are excluded in the Unicode format. When a value from the first half of this excluded range is followed by a value from the second range, we have a valid surrogate pair. We then use the 10 least significant bits of each of the 16-bit words to make up 20 bits of the result. The UTF-8 format is made of sequences of bytes. Each character begins with a leading byte, followed by anywhere from 0 to 3 continuation bytes. A special leading byte is just an ASCII byte. That is a byte value with the most significant bit set to 0. All non-leading bytes have their most significant bit set to 1 and their second most significant bit set to 0. We call them continuation bytes. When we have exactly 2 most significant bits set, then we have a 2-byte sequence. When we have exactly 3 most significant bits set, then we have a 3-byte sequence. When we have exactly 4 most significant bits set, then we have a 4-byte sequence. Validating UTF-8 requires checking many conditions. Firstly, because characters can use no more than 4 bytes, it's not possible for the 5 most significant bits to be set on any byte. We must have that the number of continuation bytes match the leading byte. And then we have a few additional constraints. We have the fact that we cannot store a code point value in the range of values reserved for circuit pairs. Though UTF-8 does not have circuit pairs, the UTF-16 format only works if these values are omitted. So UTF-8 must also omit them. Then we have to make sure that we always store a given code point value using as few bytes as possible. This ensures that a given character matches a unique byte sequence. Doing otherwise would be a security risk. And of course, it would use slightly more storage. Let us review the two formats side by side. First, let us compare how they represent ASCII. As you can see, it's rather easy to convert back and forth. It implies that you have to either insert a 0 byte or remove a 0 byte. Thus, you should expect that converting ASCII between UTF-8 and UTF-16 should be very fast. It's simply a matter of scanning the data and either removing or inserting 0 bytes. Converting 2-byte sequences between UTF-8 and UTF-16 is a bit trickier. When going from UTF-16 to UTF-8, we have to move the data bytes and insert some UTF-8 coding bits. When going from UTF-8 to UTF-16, we need to pack the data bytes and remove the coding bits. Going from 3 UTF-8 bytes to 1 UTF-16 word is similar to previous scenario. In one direction, we need to pack the data bits, and in the other, we need to insert UTF-8 coding bits. Converting 4-byte sequences is much more complicated. Thus, we should expect significantly slower speeds. Fortunately, in most documents, 4-byte character sequences are uncommon. There are many important operations we might want to do with UTF-8 and UTF-16 strings. You may want to convert them to UTF-32, for example, for internal use. You may want to count the number of characters. You may want to merely validate the input, and so forth. An important operation is to convert strings from one format to the other. For example, if your database contains UTF-16 strings and you want to post the data on the web, then you need to systematically convert it back and forth. You cannot assume that the input is valid. It could come from an adversary with malicious intentions. It could be buggy. You could have bad data. Thus, you must often validate as you transcode. It's not required, but it's an important security feature. Of course, you can avoid having to transcode entirely when you build your system, but in practice, it can be difficult because different software components require one encoding or the other. Furthermore, even if you never need to decode or transcode, you will still need to validate, which is a subset of the transcoding operation I'm going to describe. And even if you do not need any of these things, you still should know how quickly and efficiently they can be executed because they're common operations in software. So how quickly can you transcode strings currently? On a good server with some common data inputs, you might reach about a gigabyte per second using state-of-the-art C++ software. That is good, but transcoding is likely to be just one step in a series of operations, and it's already several times slower than the speed of recent disk or the bandwidth between large instances in cloud infrastructures. And we're not solely interested in its speed issue. Our experience has been to drastic reductions in the number of instructions, translating to drastic reduction in energy usage. Thus, by making it faster, you may also make it greener. So, how can we go faster? Existing software libraries are mature and highly optimized. We first observed that most mainstream processors, whether in your PC or in your mobile phone, have advanced instructions called SIMD, which stands for Single Instruction Multiple Data. Unlike regular instructions which operate over regular registers, these instructions work over wide registers and are designed to process multiple words at once. This seems to be ideally suited for processing Unicode strings. SIMD instruction sets rely on registers that often span 16 bytes. These 16 bytes can also be viewed as 8 times 2 byte or as 4 times 4 byte. On x64 systems like Intel or AMD, you also have larger registers, going as wide as 64 bytes on recent Intel systems. In our implementations, we either use 16 byte or 32 byte registers. We also avoid expensive instructions such as multiplication or instructions that require floating point numbers. Most of your software already uses these SIMD instructions. For example, when you copy data, it's common for these instructions to be put to good use since it's much faster to copy data in large blocks using few instructions. Similarly, many compilers will automatically vectorize your code. That is, they will compile it to code that uses SIMD instructions. Auto-vectorization happens in C, C++, Java, as well as many other languages. In our work, we make a deliberate attempt to use these SIMD instructions. And it is our experience that compilers can only go so far and that expert engineers can be much more efficient on specific problems. In 2008, a Canadian researcher named Cameron and independently an IBM team in Japan proposed Unicode processing using SIMD instructions. The Japanese team only published their work in Japanese and their approach does not cover the full Unicode specification. They also did not, to my knowledge, publish their software. Cameron did publish it as an open source library called U8-U16. It seems to be no longer supported, but it can be found online. Engineers are routinely using SIMD instructions to speed up special cases like the ASCII transcoding. However, there's been relatively few attempts at doing much more since 2008. Nothing in the formal literature that I could find. I tracked down an interesting effort by Goffart in 2012, and there's a more recent library by Gatilov in 2019. I'm not going to discuss further these two cases, but we review them in our full paper to appear in Software Practice and Experience, the journal. In any case, there's been little academic work on the topic, so we were motivated by this gap into research. A key operation that SIMD instruction sets support is the ability to permute bytes using over wider words using a single inexpensive instruction. Such instructions or such operation have been present in the IBM Power processor. It's available on Intel and AMD x64 processor, and is in the ARM processor that is present in your mobile phone. Though the details vary by processor type, the general idea is the same. Given two input sources, you can use one of the two inputs as a set of indexes pointing at the values in the other source. Thus, you can reorder or reshuffle the values of an array. Another way to think of the same operation is as a vectorized table lookup. Of course, if you need to move words quickly, you should either have a pre-computed set of indexes or a convenient way to compute them quickly. I call this set of indexes a shuffle mask. With the shuffle mask, you can permute the bytes within a SIMD register. If you use these instructions for vectorized lookup tables, you must similarly pre-compute a table. That is, you use one of the input registers as a table and the other one that is provided by the user as a set of indexes. Our core UTF-8 to UTF-16 transcoding algorithm works with vectorized permutation. We're going to assume that the input is valid. We're going to discuss validation later, separately. So we take a block of bytes and we find the n of each character. The n of characters can be defined as a byte preceding a leading byte. Leading bytes come in many forms, but we can detect them by first finding out where the continuation bytes are, and then we can invert this selection. The continuation bytes are their two most significant bits as 1 and 0. If you view them as a signed byte value, from minus 128 to 127, then the continuation bytes are the values that are less than minus 64. So they can be selected using arithmetic operations quickly. Once we have identified the n of each character, then we can construct a corresponding bit set. So bit set is just an integer value. For each byte of the input, we have a corresponding bit. We set the corresponding bit to 1 if and only if the corresponding byte is the n of a character. You may wonder why we identified the n of a character rather than its beginning. The problem with identifying the beginning is that for the last character in a sequence, if you only know where it starts and not where it ends, you cannot decode it. You don't know how long it is. If you're given the n of all characters, you know how long they are, assuming that your first byte marks the beginning of a character. To illustrate the construction of such a bit set, let us look at a concrete example. In my example, I have an ASCII character followed by a 2-byte character followed by another ASCII character followed by a 2-byte character followed by an ASCII character followed by a 2-byte character. The corresponding bit set is 101101101101. Treating this bit set as an integer value, I can use it as a key in a table, a flat table. So far, I did not specify how many bits I'm using. In our implementation, we use 12-byte blocks, and so we need a table with 4,096 entries in it. In the table, we store the number of consumed bytes. Ideally, we would consume 12 bytes each time, but that's only possible if the last bit is set. That is, it's only possible if we don't have part of a character at the end of our 12-byte sequence. We also have another index that points inside a table where we can find a pre-computed shuffle mask. This index to a table of shuffle mask carries information of its own. We have 3 different code paths, depending on whether we only encounter 1-byte and 2-byte characters, or whether we have found 3-byte characters, or whether we are in the general case where we might have a 4-byte sequence. Another nice side effect of having this secondary table of shuffle masks is that we only need to store about 200 shuffle masks instead of slightly more than 4,000. So we get the benefit of some compression. Overall, our tables use about 11 kilobytes, which fits really nicely in the first level of CPU cache, the fastest level. So we can go back to our example with the computed bit set. We are in a scenario where we only have 1-byte and 2-byte characters, so we would end up with this fast code path. The first step, we use a vectorized permutation. Then we apply a series of inexpensive arithmetic transformations. I'm not going to review them in detail, so you can look either our code or our paper, but they're not too complicated. Though what we described is efficient, there are a few more optimizations that we use. For one thing, instead of loading the data in small blocks of 12 bytes, we load larger blocks of 64 bytes, and we create a single bit set over which we iterate in small chunks of 12 bytes. Doing so allows us to check for some easy cases. For example, we can check whether we have ASCII bytes in one stream. So that would be a really fast code path. We can also use other fast paths for the cases where all 12 bytes in a sequence are ASCII, or they're all 2 bytes, or they're all 3 bytes. So we can add special code path for these cases, which help our performance when we're lucky. So far, we assumed that the input was valid. But in practice, we need to check the validity. We check whether the 64 bytes are correct using a fast technique we introduced in an earlier paper. We sketch our UTF-8 validation algorithm. We can recognize most errors by looking only at successive bytes, so pairs of bytes. For example, if you have an ASCII value, you know that the next byte should be a leading byte. In fact, it's enough to look at sequences of 3 4-bit words. We call a 4-bit word a nibble value. So what we do is we do 3 vectorized lookups on nibbles, followed by bitwise AND operations. It's a general strategy that I call a vectorized classification. To understand how vectorized classification works and how it can help with our current problem, let us consider an example. Suppose that I want to find all instances where the value 3 is followed by the values 1 or 2. I built 2 lookup tables, one where I set the bit corresponding to value 3 to 1, and one table where I set the corresponding bits for indexes 1 and 2 to 1. So the important thing is that the ones match. If I'm given 2 successive values, I use the first value as an index in the first table, and I use the second value as an index in the second table. I then compute the bitwise AND of the 2 looked up result. If I get 1, then I have a match, otherwise I do not. The value 1 in this instance is arbitrary. Any non-zero value would do. Of course, this can be, it doesn't look very efficient, but since I have vectorized lookup tables, it can be vectorized, and so it can be really fast. Let us look at another example. This time I will have several cases. So I have again the value 3 followed by the value 1 or 2, but then I also add other cases, such as the value 5 followed by the value 0 and the value 6 followed by the value 10. Instead of using the value 1 solely, I use the values 1, 2, and 4 as markers. I use 1, 2, and 4 because they correspond to setting the first, the second, and third bit to 1 into result. As before, I construct 2 tables. Then I repeat again. I do the lookups and bitwise AND, so the logical AND operation. From this result, I can distinguish the 3 cases depending on the result. That is, if the result is 1, then the first case is a match. If the result is 2, then the second case is a match. If the result is 4, then the third case is a match. It's not needed that the 3 cases be mutually exclusive. If it were possible the first and second case to occur, then I might have the bitwise OR of 1 and 2 as a result, so the value 3. In practice, because we use a byte-oriented model, I can recognize up to 8 different cases corresponding to 8 different bit positions. Our validation routine is based on this observation. We can do almost the entire validation solely with vectorized classification. In our case, we need a 3-way, so we have 3 tables, but it's the same idea. We just need to check that no bit is set that would correspond to an error after we're done, but that is quite fast. Constructing the correct 3 lookup table is a bit difficult, but it only needs to be done once, and you can look it up in our paper. So you only need to do it during the design of the algorithm, and it's really tiny. I refer you to our recent paper for details. The implementation is not too difficult. We take the input buffer, we shift it once, we shift it again, we do 3 lookups, and then we compute the bitwise AND. It compiles with really few instructions. Of course, in practice, we need to do a bit more work during the validation, because we must also check that we have the right number of consideration in the cases where we have 2-byte and 3-byte characters. But again, this can be done very efficiently. So this concludes our work transcoding from UTF-8 UTF-8 to UTF-16. Of course, we also need to go into the opposite direction and to convert UTF-16 strings into UTF-8 strings. It's a somewhat easier problem in some respect, but to our knowledge, it was never addressed in the academic literature, and there are few attempts at using simple instructions to speed it up. So we load up a full register, may span 16 bytes, or for recent Intel and AMD processors, 32 bytes. In the case where we have ASCII bytes, we use a fast routine. The 2-byte words are packed into bytes. We can check for this case with a few simple operations, and transformation is efficient. When the words need to be mapped to either 1-byte UTF characters or 2-byte UTF-8 characters, we first build a bitmap which indicates where the ASCII characters are. This can be done with a fast vectorized comparison. The bitmap allows us to look up in a table a shuffle mask and then to do a vectorized permutation followed by some arithmetic. The permutation maps data from 16-bit words to 32-bit words. These 32-bit words are temporary and just used during the arithmetic transformation. The bitmap also gives us the number of bytes we can consume. Indeed, we also write a fixed number of bytes, but the number of consumed bytes depends on the data. When the words need to be mapped to either 1-byte UTF characters or 2-byte UTF characters or 3-byte characters, we use a similar approach. It's slightly more complicated, and we need to build an index based on where the ASCII characters are and the 2-byte characters are. We also need to look up 2 shuffle masks and to do 2 vectorized permutation. As before, the permutations map the data from 16-bit words to 32-bit words temporarily. Overall, we use rather small lookup tables for a total of a bit more than 8 kilobytes. So this fits really nicely into the CPU cage. When we detect circuit pairs, we fall back on a Scala routine. We used to have a complicated vectorized routine that went from UTF-16 to UTF-8 that handled everything, but it involved a lot of engineering and required a rather large table. In practice, we find that there's often few circuit pairs, so it's not, in our opinion or in our experience so far, it's not worth optimizing this case so much, so a fallback routine is appropriate. Our full paper has detailed experiments, but for this presentation, I will focus on simple results using one AMD server. Note that our full paper has results on ARM-based system as well, so it would work on your iPhone. But so we compare our results against the U8, U16 library. As stated previously, there are alternatives, but the U8, U16 library is part of the academic literature. We also compare with UCI, it's the industry standard. For our test, we use lipsum text, so random looking text in various languages. For more realistic cases, we can refer you to our paper. So for ASCII, we find that we are sometimes 20 times faster than UCI. Effectively, we are nearly limited by memory bandwidth. We use the input size to determine volume on transcoding, so you should expect UTF-16 to UTF-8 to be faster in the ASCII case because it uses more bytes for storage. For non-trivial languages, as you can see, we can be 4 times faster than UCI at UTF-8 to UTF-16 transcoding. For UTF-16 to UTF-8 transcoding, the benefits of our approach are greater. The U8, U16 library is competitive, but it does not particularly shine. Our software is available online, and we encourage you to take it out for a spin. It's open source. We welcome contributions. We make it easy to use. It's thoroughly tested. Though I did not cover it during this presentation, it supports runtime dispatching. So while we have a single code base, at runtime it will check your CPU type and choose the best compiled routine. We support various processors. If you'd like more details, our full paper is available online. If you'd like to stay in touch with me, I have a blog where I regularly write about software performance, sometimes twice a week. To use our SIMD UTF library, you need a recent compiler supporting the C++11 standard. Most C++ compilers today do support the C++11 standard, so you should be okay. Next, you need to grab the code from the library. So you can take the SIMD UTF.h and SIMD UTF.cpp files from our recent release, for example. You can then drop these files into your project and you're ready to go. As an example, let us consider this simple code that will simply take a UTF-8 input and check whether it's valid. So for my example, I'm using a 4-character sequence made of the characters 1, 2, 3, and 4. Because it's an ASCII input, I do know that it's automatically valid UTF-8. As you can see, I'm using the SIMD UTF namespace. So in C++, we have namespace that distinguish your functions from the function of a library. And then I've got this simple function called validate UTF-8, which takes a pointer to a car character followed by a length parameter. And then I'm ready to go. I get back a boolean that tells me whether this is valid UTF-8 or not. This function is super fast and it should run at up to tens of gigabytes per second. Sometimes before you want to convert UTF-8 to UTF-16, you'd like to know how much storage the resulting UTF-16 string will require. So for that purpose, we've got a function called UTF-16 length from UTF-8. Again, it's somewhat similar to the validate function. We just take a pointer to the UTF-8 source, which in our case is a car pointer, and then we've got the length parameter. It returns the number of 16-bit words that we expect a UTF-16 string to require for storing the input. In this case, it would return 4 because of the simple case, the simple ASCII case. So once you've got this information and you know how much storage is needed, then you can allocate to memory and do the transcoding. This next example, code example, is basically an extension of the previous one. So again, we take our ASCII input, we figure out its length, which is going to be 4 in this case. Then we compute, we do one scan. It's very, very, very fast to determine how much storage we're going to need. Then we allocate the storage. So the SIMD UTF library is as much as possible non-allocating. So the user is responsible for allocating to memory, and that's by design because allocation is error prone, and very often it's best left to the user to determine how they want to manage their memory. So in this case, I allocate my memory using a new call, and I store the result in a unique pointer. That's all standard C++. Then I call the function convert UTF-8 to UTF-16. Again, I'm using a source pointer, a length, and then I'm going to provide an output pointer. I'm responsible as the user of the library to make sure that the output pointer points to a sufficient number of bytes, right? And in this case, I know it's safe because I've determined the correct number of 16-bit words that I would need using the UTF-16 length from UTF-8 function. I could also have allocated more memory, so this is just a strict minimum. So if you point to a very, very large region in memory, that would be fine too. And then, of course, after the conversion, it returns how many words were written. In this case, of course, it's going to match my expectation. For one thing, because I've got a valid string. If my string was not valid, then this would return 0. So there would be, it would detect an error. And also, if I had allocated much more memory just to be safe, let's say I had allocated a gigabyte, and I was interested in figuring out ahead of time how much memory I needed precisely, then this return value would be very useful because it would tell me exactly how much memory I used actually. Of course, you can go in reverse. So you can just do the same thing. So you can use an ASCII string, a 4-character ASCII string, but this time I'm going to allocate it using UTF-16 words. So my pointer there is going to point to 4 characters, but each character is going to use 16 bits. Again, I can check and validate it. In this instance, because my input is ASCII, I know it's going to be okay. It's going to say that it's a valid UTF-16 string. Again, just like in the UTF-8 case, I can try to predict the output size of a UTF-16 to UTF-8 transcoding. This time the function is called UTF-8 length from UTF-16. Because in my simple example, it's just ASCII, I know that the answer is going to be 4. So I have 4 16-bit words, and if I convert them to UTF-8, it's going to output 4 bytes. Finally, I can do the full routine where I start with my UTF-16 input. I try to deduce how many bytes I'm going to need for storage after the transcoding. I allocate the memory that I need. In this case, I use a new car operator, and I store the result in a totally standard C++ unique PTR. You don't have to use a unique PTR. This is just my doing. You can store it wherever you'd like. And then I do the conversion. Again, the conversion in this case is going to be non-allocating, so it doesn't throw, there's no exceptions, and there's no memory allocated, so it's not very error prone. If the input is valid, then it's going to return the right answer, so it's going to return, in this case, 4. If the value was not valid, then it would return 0, indicating an error of some kind. Again, to convert UTF-16 to UTF-8 function takes a pointer to my input. In this case, it must be a car 16 input. It needs a length parameter, and it needs an output parameter. Again, the output parameter, I need to have allocated a sufficient number of bytes. So it must be at least 4. It could be more. And then the whole function, as I said, in this case, would return 4. So there are more functions in the library, but this is the core part of the library. And as you can see, or hope you can see, it's relatively easy to use, and that's by design. We try to keep it really simple. There are no objects, there's no fanciful exceptions to manage. It's all straightforward. Thank you.